this talks about the Go programming language. In case you missed it, sometimes people are like, what are we talking about here? So we are talking about Go, the language, hence the gopher on the slide. And from the perspective of people who are Java programmers, are people in the room Java programmers for the most part? Yes, no? What you're shaking your head like with passion.
I'm actually a Go programmer.
You're actually a Go programmer, so you can get this talk.
JavaScript.
So this is good. And I want to preface this that I am very much a Java developer myself. I am not a Go expert, right? And I don't know how well these slides will play here. They play great in Denver. But I'm not a Go expert. I'm actually just learning a little bit about Go. And, you know, Tim's a Florida guy, so maybe some people around here know this relationship between a quarterback that actually can play football and one that maybe can't so much, at least not in the NFL. But this is kind of my tenuous relationship with the Go programming language. Like, I think I can write code in this thing, and I can do some interesting stuff, but then you start to ask me the low-level details about how the slicing mechanism works, and I might fumble there a bit. So in some cases, I might punt on a question, is more than anything what I'm getting at, but hopefully you're still going to get a valuable broad picture of why the Go language exists, how it works, and as a Java developer, why is that interesting to me? Which might lead you to, why did I learn this in the first place? So, as I've said many times throughout the week, I work on Cloud Foundry. I've worked on Cloud Foundry for going on 2 years now, and if you look at the architecture stack of all the various components, January of last year, color-coded by language, you see that most of this platform is written in Ruby. And I don't know how many of you have hung out in my sessions earlier, but you may have heard something about my love for the Ruby language, my deep, deep love for the platform that is Ruby. And if you follow me on Twitter, you've even seen interesting stuff to that effect. You fast forward 1 year, and oh my, the Ruby is disappearing and has been replaced with quite a lot of Go, and new components have been born in Go. And again, I came to this from a Java background perspective, working on this platform. It's like, well, I need to understand how it works and be able to work on it. So I probably need to know the language that it's written in. Of course, I'm like, hey, I just got done learning Ruby. So these things happen. And I'm not really going to go into why the switch. There are a couple of videos out there on YouTube that you can check out. Most importantly, Mike Gahard's video, Go Within Cloud Foundry, which is from the Platform Cloud Foundry Conference, I guess not this past September, but previous September. It was up against Spring 1 co-located, and he talked about why we chose to use the Go language for various tasks and what value we got out of that. And then Ansi Fakori gave a talk at CF Summit in June, where he was talking about Diego, which is our new container scheduling system that we're going to use within Cloud Foundry, but you could just generally use to schedule and run things like Docker containers on our infrastructure. And in that talk, he actually, said this is all written in Go, and here's some of the things that we got out of that. But I'll leave that as an exercise for you. The problem with this talk is there's too much in it. I wanted to talk about a lot of different things. And if we get too far off on specific rabbit trails and syntactical issues, we're going to miss like half the talk. This has actually happened before. We have nixed literally the whole back section of it because we spent like 20 minutes having a really great discussion about how slices work. But ultimately we're kind of like, oh man, we don't get to see this other stuff. So if I say, you know what, we're done with this question, we got to move on, that's why, because I want you to be able to get all the material. So, first of all, hello world, got to start there, obviously. This is how we learn programming languages. We do hello world. A couple things to point out. All code goes in a package. Yeah, we're used to that from Java. No, really, all code goes in a package. You can't actually leave the package statement off. If you do, your code won't compile. So none of this default package business anymore. How do we gain access to stuff in other packages? Well, we import those packages. Okay, this is also familiar. Couple things to point out here. When we import things, we're actually gaining access to exported things from the thing we import. And when you start to think about visibility, there's really on or off, exported or not exported. We'll get more into that. By the way, I want to make it clear that this FMT is not format. When I read that, I would read it as format, and then I was told that I was incorrect and actually blaspheming. This is funked. Say it with me, funked. Okay? You have to read this as funked, or people will look at you funny as you're talking about Go code. So there's a little language change we have to make there from a speaking point of view. We have functions. Function definition main is going to be the entry point. Okay, this feels again fairly normal. We're calling here an exported function. How do I know it's an exported function? Because it's got an uppercase P. Case is actually important in this particular aspect of the language, which is fun. So that's our hello world. Now we're going to do a little more syntax, just so that we have enough context, so that when I start talking about the why of this language, you're like, oh, actually I kind of understand that there is this syntax that he's talking about, and have some context. So basic sets of things, more about functions. As a Java programmer, this drives me crazy because I'm constantly going back and forth between Java and Go. And of course, Java, C, languages like it, the type comes first. In Go, the type comes last. So we have to get used to not typing int x, but typing x int, which, believe it or not, if you're switching back and forth between the languages, you'll read the compiler error message and you won't understand it because you think you're writing Java subconsciously and you're really not. So that can be frustrating. Same thing, return type. The thing to point out here, and I don't arrow this, is that we have keywords for practically everything. And the reason that we have keywords for practically everything is because it makes the language incredibly easy to parse. And what can you do with a language that's incredibly easy to parse? You can write lots of your own tooling. And so as it turns out, a lot of the syntactical choices that were made in the language were specifically geared toward making it easy to write tooling for the language. And as such, you see this really huge sort of community supported tool building effort that's going on. I can't count the number of times a week that a new language development tool in the community is born around one of these ideas, which is quite cool. You don't see that as much in the Java space, at least not these days. Variable declaration. So var keyword. Also something that's new to us from a Java perspective. Declaring multiple variables with commas makes sense. You can do type inference, so I can leave the type completely out. One thing to point out, zero valued, not nil. Now, this is not a good example here, really, because we're not talking about pointers, we're talking about a value here, but at any rate, there's no such thing as when I declare something, for the most part, at least as you're dealing with types that are built into the language, of that thing starting out as a nil reference. It actually starts out as whatever the zero. So if you create a string, for example, Java, we get a string, it's null to start with unless we initialize it to something. In Go, we get empty string. Int, we get 0, so on and so forth. And so you get that out of the base types, and of course the recommended practice is as you're designing your own types to have them also initialized cleanly to a 0 value, because that allows you to kind of have solid expectations throughout the program. This is the most idiomatic thing on the whole slide, though, is this shorthand for declared and initialized. So we're bringing Pascal back with the good old colon equals operator, and getting to drop the var keyword as well as drop the type information at the same time. Okay, lots of types. I'm not going to go into these too deep, just to give you an idea of what's out there, all the various flavors of ints and unsigned ints that you would expect to find. Roon's pretty cool, name for an int32 that represents a Unicode code point. Everything's Unicode, so we don't have to argue about that, which is quite nice. And you don't get to write an example of creating complex numbers in Go because they're already there, which is also interesting. So if you're doing lots of of math with imaginary numbers, you're set. I don't know if anybody's got a demand for that in the room, but I thought it was kind of cool. Constants are these weird beasts. So we have a const keyword, great. And const can appear anywhere a var can, so that's expected. What's kind of interesting is when we start to do stuff like this. It's like I've got a const that's actually based on an expression, and as it turns out, it looks like it has a type, but it doesn't have a type. Consts don't get a type until they're given one. So I can explicitly give a const a type. So I want, in this context, for D to be an int64, and it becomes an int64. But if I use it in a context that expects a specific type, it will be, I think the right word is coerced, but it will become that thing. So Stine expects a float 64, I believe, and it's going to become one there. So why would you do this? Why would you have things that are untyped but then become typed in different contexts? Anybody have an idea as to why you might want that? I didn't either. So then I started kind of digging into this a little bit, and basically the idea is that I want to be able to create constant variables. That's a weird way to say it, but a constant thing that I don't have to know all the context in which I want to use it up front. So I've got this thing that's constant across my program, and yet I can use it in different places without actually planning all that out. So it introduces a little bit of flexibility into the language that might otherwise not be there. It's like if I have to type all my constants up front, then I have a limit to the context in which I can leverage them. So it's just a small little feature, but and you see lots of this throughout Go, these little features that don't seem like they're very consequential until you look, oh, there's this cascading effect there.
So you don't need a 32 this is 45 or something.
Yeah, exactly. Exactly. That's exactly right. Okay, loops. So another interesting decision point in Go is, which is inconsistent across the choice. There's no consistency that you can just rest upon in terms of, okay, I really think that Rob Pike always wanted to do this, and then I go, no, he didn't do that here. So one of the things that is like, if we don't need it, let's not put it in the language. So for example, if I can accomplish everything that I want to accomplish with a while loop, with a for loop, then why do I need a while loop? So there is no while loop. There's just a for loop. For is the only loop in the entire language. And you can have a single condition for, which is equivalent to a while. Great. You can also have a classic initial condition after. And if you want an infinite loop, you just for. And if you break or return, then you get to get out of that guy. So it's like, you know, we do these things anyway, so let's just make them first-class features in the language and get rid of some of the crufty bits. Like, I can create an infinite loop with a for like this in Java, but I have to have parens and double semicolon. It's just silly. Conditionals. Here's another one. No parentheses around your conditional expression. Not optional parentheses, no parentheses. You put parentheses there, it will not work. Now you can still group expressions, but your outer bounded expression cannot be parenthesized. Obviously else's are optional, that makes sense. There is this syntax where you can have a statement and a conditional built in together. So I'm setting num to be 9, and then I'm doing some checks on that throughout. Now obviously reading this code is kind of silly. We know this one will never succeed, but this one will, and this statement, what it declares is actually a variable, is actually available throughout that whole scope. Now you get to switch statements are really fascinating in that they look like your regular switch statement, but they're actually this switch statement on serious steroids. So no more of this, it has to be a compile time constant to switch on the thing. Like we really just begged and pleaded to get switching on strings in Java. And finally, it was determined that there's a way we can do this without breaking Java going all the way back to 1.1. And we got it in the language. And here it's like, switch on anything you want. You can switch on, here, I is a number. You can switch on an expression. Say, oh, time.now.weekday. Case Saturday or Sunday, print this thing, otherwise print it's a weekday. That's interesting. What else can I do? Defaults. Oh, by the way, look, did you notice there are no breaks? These don't fall through. Because we know that every time we write a switch statement, we put the breaks there. Nobody actually uses that fall through feature, so let's just get rid of it. And then the ultimate, switch on nothing at all. You just switch and write cases, and it's an alternate way to express if-else logic. So if, to you, the thing you're trying to express looks cleaner syntactically and readability-wise this way versus a standard if-else, just use it. Okay, so that was just enough sense. You should be able to read most Go code now. One of the cool things about this language is that you can pretty much pick it up in a day. So just a case in point, at Pivotal Labs, where we work on Cloud Foundry, we had like 2 Go programmers. Within a few weeks, we had like 10 or 12 Go programmers who were fairly adequate in the language. You can read the entire spec in about 2 hours and actually understand what it says. There's just not a lot there. And it really kind of bleeds into this quote from Justin Searles, this idea that writing boring code that does exciting things is actually cooler than writing exciting code that does boring things. And this really fits into the whole Go kind of a lexicon here. It's not an amazing, modern, feature-rich language. It was not designed to be the ultimate new programming language that has the greatest functional, hybrid, object-oriented, monadic structure, right? I'm joking here a little bit. It's supposed to be funny, guys. Wake up. It's lunch. It's after lunch, I know. It's actually kind of boring. In fact, Google for Golang and boring, and you'll actually find articles and blog posts that start with that as their premise. But they're not hating on Go, they're actually loving on Go because it's boring. So if boring is your thing, you're in the right place. Basically, there's this idea, you kind of make up this iron triangle analogy that, I can't get efficient compilation and I can't get efficient execution and ease of programming all in the same spot. And again, focused on systems programming, it's kind of funny hearing these guys talk like what we think of web server programming, which used to be called server programming, used to be called systems programming. Not thinking about writing fancy web apps. This is not a Rails kind of idea, but like writing web servers, writing high throughput message bus type software, writing cloud platform software. This is why you see things like Docker and Cloud Foundry and all the HashiCorp projects. These things are being written in Go because it's nice language for that particular sweet spot. So at Google, they're kind of in this wrestling match of, well, the systems programming languages that we have, they kind of suck. We've got things that take 45 minutes to compile in C++. And what we'd really like to be able to do is to get something that feels like programming in Python, where we can get really fast feedback and really good flexibility. And so people start moving over to Python. And I'm not going to get into whether this is actually, I'm not going to take sides in the debate over static typing versus dynamic typing and safety and which one's actually better. You can talk to Stu if you want to get into that. But these programmers believed that I'm giving up safety by moving to dynamic languages. So what they really want is a language that has both. So as the story goes, you've got these 3 genius level guys sitting in a room. What have these guys done? What did Rob Griesmer do? Anybody know? Anybody ever use the hotspot Java compiler? Yeah, he wrote that. And then he wasn't done. He decided, you know what, I want to do something else. I think I'm going to write the V8 JavaScript engine. So yeah, he's pretty smart. Rob Pike's only written like 4 operating systems in 4 languages or 5 languages. And Ken Thompson only like made Unix, you know, or at least he had a huge head. So you get these 3 guys in a room and they're bored. And they just kick a compile off 45 minutes. And every time they make a change, it's like, let's make a language that doesn't suck for what we're trying to do here at Google. And they start sketching out Go on a whiteboard during one of these compile sessions. And this is the way they tell the story. So a couple years later, you've got Go released as an open source project. A few years after that, you've got a 1.0 release with a promise of backward compatibility for the spec, which means that people are going to want to adopt this. I'll hate on Scala here a little bit. Every time a new version of Scala comes out, nothing works anymore, and you have to change your code. You don't have that in this space, which is kind of a nice thing. So why did they do this? What's their guiding principle in building a language like this? Software engineering in the large. So think millions of lines of code, thousands of engineers, all working off a single tree of all the software, big custom build system with on a cluster, you know, zillions of deployment machines. This is what they're doing. And so they decide, what if we were to create a language that optimized not for a set of features or being a pure functional language or the best object-oriented language, whatever. Let's create a language that's optimized for getting our stuff done. And try to make it a little less slow, a little less clumsy to get code written, and make it possible for us to accomplish Google's kind of goals. So this statement, you know, Go is a programming language designed by Google to help solve Google's problems, and Google has big problems. That's sort of the guiding statement for why this language is the way it is. So you look at the compiler, you look at dependency management, you look at syntax, naming, garbage collection, everything in the language. Every decision point was guided through this. So you start to ask, you know, it's like, why is this thing not in Go? Here's the answer. You might have to think about it a little bit and figure out, okay, how does this relate? So, like, one of the most controversial things is there's no generics in Go. And people just, it really makes people angry. If you read some of these threads about why there's no generics in Go and it's this evil thing, and there's all these implementations out there of people trying to get it done. And some of them are actually kind of comical, believe it or not. But it's not there. And why is it not there? Because it didn't actually carry them towards this end. And there were other things that did. So goals: safety and efficiency of a statically typed compile language, productivity and feel of a dynamic interpreted language, or have my cake and eat it too is what we wanted. Plus, a systems programming language that's built for modern compute environments. So when was the last systems programming language actually created? Like 76 maybe? Was when C++ came on the scene, was it? Am I getting that right? At any rate, before multi-core processors, before network systems were ubiquitous, before massive compute clusters were mainstream, and before there was a web. Now, we can do all these things in C++. We can do all these things in Java, but for the most part, they're actually bolt-ons. They're library features. They're not first-class support in the language for dealing with and thinking about these things. And that's one of the differences. One last bit, and I borrow this from Mike, is that Go's not a gigantic box of Legos. Meaning, you know, you have the gigantic box of Legos and you can build whatever you want. And it sort of looks like the thing that you wanted to build. This is how I like to think about Java. Massive ecosystem of things that you can go grab and construct a thing. But you kind of feel like you're gluing stuff together to get things done. And it's what I want, but you kind of look under the hood and you're like, it doesn't look like it was really thought about in this way. What the goal was a kit. It's like, let's build a kit for system software. So if I want to build X-Wings, then I get X-wings, and they actually look like X-wings. I go looking for things. I need web stuff. It's in the standard library. Crypto stuff, standard library. JSON marshalling stuff, standard library. Operating system interaction, standard library. And there's this huge emphasis in the community on not building frameworks. It's like, let's not build big behemoth frameworks that do lots of stuff like you find in Java and Ruby and Node. Rather, insofar as it's possible, embrace what's in the standard library, and where it's not, build small composable libraries to get things done. So anytime you see anybody announce a framework for Go, it's like there's this visceral reaction in the community. And people kind of push back against it. And I said, why are you doing this? I'm not saying it's good or bad, but it's what I see. So there's some whys. Now let's get into the interesting stuff. Differences from Java. 4 buckets. The first bucket's just a bunch of stuff that wouldn't fit, didn't really have a theme associated with it. Then talk about packaging and modularity a little bit, talk about OO a little bit, talk about concurrency a little bit. Okay, so features and idioms. First thing, how many times have you wanted to return 2 things from a Java method? Lots of times, right? And so we build all these hacky kind of funny ways to get that done. Why don't you just do it? So that's the decision that was made. So we can put a parens and list of return types. We can return a set of things. And so A, comma, B, vals, first return value goes in the first variable, second goes in the second. Everything's happy. We can just do something that we want to do. And first class representation of the language. We could have just done A here, and we would have gotten just the 3. What if I just want the 7? Underscore ignore. And that allows me to get to that. Go has closures. Closures are nice. So I can close over that state and return a function that captures that and does stuff with it. So that when I say int sync, I get a function back that will give me next int, next int, next int, do it again, starts again. We don't have closures in Java. Wait, I thought we had lambdas. Lambdas are not closures, unfortunately. So I've got this code here. I've got a functional interface that is an int returner. An int returner, I've got this thing, I've got a lambda that returns a thing, increments it, yeah. The only problem is it doesn't compile. Darn it. Anything that you reference inside of a lambda has to be final or effectively final. So this code doesn't work, even though it looks really awesome. Like, it would be awesome if this worked, but it doesn't. You can sort of do this with strings. So I've still got my functional interface here, except I stream.iterate from 1 with a method pointer to stream inc that does my number plus 1 stuff, get an iterator from that, return a lambda that inc. And it kind of sort of looks like the code that I want, but not really. Awful lot of work to get that done. Very simple thing. Just want to return a function that increments a number from the enclosing state. That's all I want to do. Is that too much to ask? If you want to maintain backward compatibility, yes, with every Java that we've ever had. Okay, so list-like types. There is a type called a slice in the language. And you make a slice, and you get a size of this thing with 0 value. So this is a slice of size 3, empty string, empty string, empty string. I then can put things into those cells. So now I have A, B, C. I can get the value back out, so that will give me back C. If I want to take 2 slices and put them together and make a bigger slice, I use append, and that's actually going to do a copy of the original plus whatever I append to it, okay? So S equals append S with a D is going to give me A, B, C, D. The original S goes away at this point. Now if I assign it to another variable, I would still have both. So these are actually effectively immutable structures. I can also take the length of one of these and then copy it. So if I say, give me C as a slice that's the same size as S, I can then copy S into C and get the same result. Again, this is an effectively immutable thing. We're not actually changing data structures. Slicing is different though. So when I say L is S2:5, what that's doing is saying, give me a window into S that starts with index 2 and goes up to index 4. So 5 is exclusive. If I then go in and start changing values in S, they're also going to be reflected in L. So whereas copy and append was actually, I got a brand new data structure, this is actually a view onto an existing data structure. Same thing here, 0 inclusive up to 5. If I left out the end barrier, I would go to the end, so works as you would expect. Here's a slice literal. Maps are built into the language as well, so I can make a map of string to int, which is nice, and put values into it using basically the same syntax as we had for arrays. Get things back out as you would expect, take the length of it. Principle of least surprise here. Delete keys from the map also. Here's one of those optional second returns that we didn't really know was there. So I'm underscoring, comma, PRS is access a key. The second value indicates presence. So if that key is present in the map, PRS is going to be true, and then I'm going to have the value over here. Otherwise, I'm going to have false, and depending upon whether it's a pointer or a value type, I'm going to end up with a 0 value or a nil in the first one. I'm saying that right, aren't I? Okay. I always get that one mixed up in my head. And I'm alluding to something that I haven't said explicitly, is that there are pointers in Go, but they're not the scary kind. Like there's none of the pointer arithmetic stuff going on. Think of it as, what if everything in Java could be expressed as a value and a reference? That's basically what you're dealing with. But as you start to switch your mental model back and forth between the two, you have to realize that the rules change in terms of what values can actually be. Map literals as well, fairly simple. Okay, other cool looping stuff. So there's this range keyword, and what range will do is essentially give you the equivalent of a for each. So here we're starting with a slice, and we're going to get in the first return value the index, and the second return value we're going to get the value associated with that. So we don't have to have like each and each with index, it's all just in one. So here I'm keeping both. First one I was discarding. Here I'm doing this with a map. So I can range over maps as well and get key value instead of index value. And we'll see range pop up again a little bit later on. Now let's get into some interesting controversy. There are no exceptions in Go. Does this make anybody angry that there are no exceptions in the language? Who really likes exceptions? Anybody? Seriously? Nobody really loves exceptions in here? Who likes error codes? Like I call a function in C and I get back some value that doesn't seem right, and I'm like, what is this? Oh, that's an error value, and you should just know that because it returns this. So there's like this spectrum of we return odd things to indicate errors versus we have this massive, explicit, statically typed exception handling mechanism with special syntax and semantics to go along with it. So Go's kind of taking a middle ground here and saying, okay, we're going to have errors represented as a first-class thing in the language, and so there is an error type here. We're going to treat it just like a regular value. So conventionally, if you want to indicate that a function can have an error associated with it, you actually just return an error as the last thing. Create a new error, pretty easy. Errors.new, give it a string. Really, the only thing that's special about an error is that it has a message associated with it. If you don't want an error, you return nil. Cool enough. We get into our code, And this is where it becomes very idiomatic to see this if statement, then condition. So we're saying if results, comma, error, call the function, and the error is not nil, then handle the error condition, otherwise handle the success case. And this is pretty much how 99% of the Go code that you're going to read is going to look. Error handling at the call site. Why do you think you might want to do this? Why would you want to handle errors this way?
Execution speed?
Could be that. Think back to the guiding mantra, though, behind the language. You've got lots and lots and lots and lots of code. And with lots and lots and lots and lots of code, you can have lots and lots and lots and lots of errors. So rather than with Java where I can throw an exception, and if I handle exceptions in various different ways, I can have errors actually propagating throughout the system and actually have them appear in front of me, and I have no freaking clue where they came from without spelunking through a call stack. Whereas here, I'm forcing you to either deal with the error or swallow it at the call site. And very easy to kind of spot where errors are not actually being dealt with. Because if you reference code and you don't actually do anything with it, your code won't compile. So really the only way that you can throw this away is you can underscore it. And so it's very easy to put a check in your code that says, okay, if anybody's underscoring errors, flame them and not allow them to actually write code like that. So it's literally a psychological effect to force you to think about and deal with your error conditions when you encounter them. And if you're building big, complex, massive software, that's actually a really good thing. You can make your own error types, and I'm going to introduce type creation and methods before I actually introduce them, but just, you probably imagined eventually that we get to a struct. And we're creating a type here that's a struct, and implementing on it a method, which is just a function with a receiver argument, that makes this thing an error. And I'll tell you why that makes this thing an error a little bit later, but I don't want to give too much away until we get into OO. But it's just so, because I did these two things, this now can be used in place of an error such that, oh look, this thing returns an error, but I'm actually returning a pointer to an instance of my arg error type, and goes happy with that. And in fact, it's so happy with that when I get into my client code, there's really nothing special required to deal with that custom type if I only want to think of it as just another error. Now, if I want to think about it as the special error type, then I need to do what's called type assertion. So here's another one of those places where this looks like I'm calling a method on E. I'm not calling a method on E at all. So the dot operator is overloaded a bit. What this is doing is saying, I think this is a pointer to an arg error. Try that. If it is, OK is going to be true, and this is going to have the reference populated. If it's not, then OK is going to be false, and that's going to be nil. So it's kind of like a safe cast operator, if anything else. And so once that safe cast succeeds, then I can start to say, okay, cool. Let's interact with the arg and the prob that we created earlier. Okay, last thing in the grab bag bucket is what I call semi-automatic resource management. So I'm alluding to the ARM blocks from Java 7. I can declare resources in the try and they're automatically closed. So it has something that kind of gives us something similar to that. So here I've got a couple functions: create a file, write to that file, close that file. I need to make sure all these things actually happen. So create, do stuff, close. Need to make sure all that matches up. What I can do in Go is called defer. I can actually have my create and my close side by side. And when this function actually completes, it's going to execute that close file function. Now what this is actually doing is building up a stack. So I can defer multiple times. And every time I defer, I'm pushing down, pushing down. When the function completes, I pop that stack and start executing all those functions. If this thing blows up in the middle of it, it's still going to execute all those functions. So it's roughly equivalent to a finally. This is something that I've gotten into some arguments with real hardcore Go programmers about, because there's actually semantics that I don't understand well enough to agree or disagree with them that no, it's not really a finally because it's this. I haven't really gotten there yet. For all practical purposes, all the experimental code that I've written, it works like a finally. So obviously there's some edge cases there that I'm not familiar with, but that's the way I think about it. It's also the way Ken Sipe thinks about it, for that matter. So you got two NFJS speakers that think it's like finally. Maybe that means something. Okay.
Is it always
Yes.
a function, or
I'm sorry?
is it always a function, or can you have a block?
Can I have like a block?
Scope
Instead of
No, it's always at the end of the function. It's not block scope.
So if I have multiple, I have to make new functions. If there, for some reason I want to do the close before the method ends.
If you want to do the close before the method ends, you can just call it.
Okay, so that,
Like this is just saying, I want to make sure that that happens.
yeah.
So make you call it. And there's actually a cost to this. When there was a great talk at GopherCon earlier this year that Derek Collison gave. He wrote, among other things, a really high throughput message bus in Go, and he talked about the cost of defer. And if you're really striving performance, you actually don't want to use this. But yeah, if you want control over when close file executes, then it's better just to write the code that you want. This is sort of more of a convenience feature. Okay. Let's get into packaging and modularity. TLDR, Java's complicated, Go is simple. I'm not saying a negative or a positive statement here, I'm just stating fact. And the way I approached this was, okay, I'm going to pretend I haven't been a Java developer for 15 years, and I'm trying to understand how Java packages things for the first time, and then compare it to similar experience in learning this from Go. So I start to think about Java packaging. Okay, so as far as I can know, every class is in a package, even the ones that don't declare their package. They're in the what package? The default package. But code that's in a default package isn't actually equivalent to code that's actually explicitly put into a package. There are things that don't work. Gosh, that's confusing. Then I can import classes explicitly. I can also import all the classes in a package with a wildcard. Okay, think about what that does. And then there's these static import things that are different from regular imports, and I have to understand what those semantics are. And I can do explicit and wildcard imports there as well. Not that any of these things are hard to grasp and understand, but there's a lot here you have to think about and what's going on. We do all this subconsciously. But if you're a new programmer, it's like, oh my gosh. I remember my very first, I actually took a course that was Java in college. And I remember the first program, Hello World, was like, okay, all this stuff up until the end of the main method declaration, you just have to write that code for your code to work. I'm not going to try to explain what it does now. It's like, to me, right off the bat, it's like, oh, complexity is here. Because there's stuff that they won't even explain to me because it's going to be too hard for me to get going. Go, a little bit simpler. All types and functions belong to a package. Every source file must declare its package or your code won't compile. And you import packages to gain access to exported members. There's no wildcards versus not wildcards. It's either there or it's not. Fine, that's cool. Now let's talk about scoping. So we have all these scopes. We have public. What does public mean? Any class in the same package, any importing class in a different package can see it. Okay, cool. Then we have default, but we can't even agree on the name. Is it default? Is it package private? I don't know. The spec says one thing, the community says another. That means any class in the same package can see. Cool. But that wasn't good enough. Because we wanted subclasses to be able to see things if they were in a different package from their parents. And so we created something called protected, which is less protected than default. Any class in the same package, any subclass in a different package, see. Private, okay, this kind of makes sense. No other class other than I can see it. How do I know what scope something is? I have to go find the thing, where it's declared, and actually look for that scope. Again, we do this subconsciously, but if you're coming into this like new, it's like, what does this all mean? When do you choose which is good, which is bad? Because like, you'll get people who will say, oh, you made that package private, that's evil. You shouldn't do that. Why? Because it's just evil, right? Anybody ever have these conversations? I've had this conversation. Go. It's either exported or imported. Or exported or non-exported, sorry. So exported, if I import the thing, I can see it. How do I know if it's exported or not? It starts with an uppercase letter. I don't have to go look for a declaration. If I'm reading code and I see a symbol, I know immediately if that symbol's exported or not. Non-exported starts with an underscore lowercase. I know immediately what it is when I see it. That's nice because now I'm not reading through. So Go code tends to be a little bit more verbose. There's not like all this terseness that we're seeing in some of these other languages. There's a balance there. But I'm reading through lots of code. I see something. I'm like, oh, which one is this? I know instantly information that I would have to actually go searching through a file to find otherwise. So there's yet another choice made for readability in terms of large code bases.
So that's enforced by the compiler.
Everything's pretty much enforced by the compiler.
So that also means you cannot use any character. I mean, there are letters that cannot be expressed in uppercase or lowercase.
Right. So I have so example of one.
German.
Yeah. So I haven't actually written any German code. So.
But they wouldn't be able.
But I'm sure there's something that makes sense to deal with that. I just don't know what it is. That would be an interesting question to answer, actually. Lots of, well, yeah, I mean, where case is kind of not really relevant. Interesting. I hadn't thought about that. That's cool. Or not. I don't know. Naming. This is where it gets silly. So, oh, go ahead.
Best practices to use the lowercase or underscore?
I don't know that there's really a best practice. Most of the code that I see doesn't use the underscore. Actually, underscore is probably there to help in a lot of those situations that you're talking about, but I have not personally seen, I don't think any of the code that we write uses the underscore. We strictly use case. So, naming. So you read the spec for Java conventionally, the directory path and the package name for code match up, although that's not actually required. All the tools expect it, but the spec doesn't make you do that. Package paths do not have to be unique at compile or runtime. Now this is something that I will say is evil. The fact that I can have, at compile time, two different jars that have the same class in them, same method name, different signature. I write code that depends on one signature. I swap the order of those things in the class path, and my code compiles this way, but it doesn't compile this way. That's evil. At runtime, we know that whoever gets loaded first wins. So if you have, as an exercise, take your biggest application that you're working on and go look at all the jars in the class path and see how many of them are duplicates that you didn't know about. And then you realize, oh, my code actually works by coincidence. It's that the class loader is behaving this way and it hasn't hurt me yet that my application is actually working. These are evil things. Don't get me, I don't hate Java. These are evil things. This URL thing, so package, reverse the URL, that's the package name for my code, so com.mattstein, mattstein.com, cool. Except there's no code there. Okay. Go. Same conventional correspondence between directory paths and package names. The tools expect that, but package paths have to be unique. across what's called a go path. Go path is your workspace where all your code lives. You cannot have duplicate paths in there. You cannot have the situation of my code compiles this way, but it doesn't compile this way. It'll only ever compile if all those are unique. When you refer to imported name, package names don't have to be unique. So I could have a.foo and b.foo. That's okay. You always qualify. So if I imported database/SQL, I'm always going to have SQL.db, not just db, unless I .import it, which is evil. That's one of the things that's actually evil, but people don't really explicitly tell you why it's evil, other than it can make the code less readable, which is pretty much good enough. Corresponding conventions is there, except there's actually code. So when I say that I have code at github.com/joefitzgerald/cfenv, there's a command called go get that will actually go through your code and say, here's all these URLs. I'm going to go out to those URLs and I'm going to find code and pull it down. And that's actually how it works. For all practical purposes, the package system is the web. And Git, Subversion, Mercurial, and Bazaar are all supported as backends to that. There are consequences here, but that I'll talk about a little bit later on, but it is pretty cool. A couple other miscellaneous evil things that Java admits: circular package dependencies and dead imports. Go will not have either one of these. You have circular package dependencies, dead imports, your code won't compile. Okay, moving right along to object-oriented stuff. Go takes a pretty unusual approach to object-oriented programming. You can have methods on any type, but there's no classes. There's also no prototypes. There's nothing that looks like an inheritance hierarchy, because there's also no inheritance. Completely flat type system. No subclassing, nothing like that. Why? Basically because we didn't think we needed it. It's like, yeah, people have built really nice, successful systems with type hierarchies, but that doesn't mean you have to have type hierarchies to build really successful systems. So let's see how far we can get without things like generics that I mentioned earlier, without things like type hierarchies. And as it turns out, it's been pretty successful. And we've actually had this advice in the Java world for a long time. So you crack open effective Java item number 16, you see all these reasons to prefer composition over inheritance in a language that has both. So they're actually just taking that advice and saying, you know what, we're just going to not allow this and see what happens. So we can create types. So type keyword, give it a name. Is this type exported or not exported? Exported, good. This type is a struct. You can actually define others. I can say type foo int, and I now have my own my very own type that looks like an int, although it's not interchangeable with an int. Add stuff to it. Uppercase exports apply here too. So if I import the package that holds point, in this case I would be able to see point.x and point.y. If they were lowercase, I wouldn't be able to see them. Methods are, again, just functions with a receiver argument. This is actually true in all languages. It's just that you don't get to see it. In most of them, it's obfuscated away. You can define methods on pointers or values. So this one's defined on a value. So if I have an instance of a point and I call translate, what do you think happens to P inside the method? What is P? I remember pass by value, pass by reference. What does this end up being? Pass by value. So I get a copy of P every time I call translate. And I operate on the copy. The original's left unchanged. Now if this has been a pointer to P, then I get a reference to the instance, and if I were to do things to it, then those would actually be reflected back home. So I can implement both of these. I don't have to choose. The idea being, you know, it's like, oh, methods are useful generally, so let's make them available in all contexts. So how do we create what feel like hierarchical type things? So we're going to do composition instead. Here's another interesting language choice. There's really no such thing as an enumerated constant in the language. The closest thing that I can come up with is this idea of using iotas inside of a const. Now, I cannot remember for the life of me, and I always forget to look it up, where iota keyword actually came from. When I watched one of Rob Pike's talks, which, if you want to be educated and entertained at the same time, go watch a bunch of Rob Pike's talks. But he at one point lists all the languages that influenced Go. And I can't remember, maybe it's Eiffel or something like it, but that's where iota came from. But essentially what this does is, inside of a const declaration, iota starts at 0. Every time iota appears, increments. And so this ends up being blue 0, red 1, green 2. And you can use iota in the context of an expression and do calculations on it as well. So it's an interesting way to build this thing up. Now, color point composes with points, so I'm embedding types inside types. So now I have color point type that actually has a point inside of it. Great. So I have points and I have color points. Great. I have a problem. I have points, I have color points, and color points are like points, but they are not points. Meaning if I want to do something that makes sense, like let's compute the distance between a point and a color point, I can't actually do it because they're not in a hierarchy, there's no polymorphism in play, this isn't going to work. So what to do? This is where one of the coolest features in the language that people don't understand why it's so cool, but you have to think about it. Interfaces. Interfaces are amazingly good. Interfaces group behaviors. So I have another type called an interface. This happens to be a positioner. A positioner knows how to calculate its coordinates and give me back a point representing them. I also have a distancer. A distancer can calculate the distance between me and another positioner. Now, notice the "er." In Go, it is idiomatic for interfaces to end in "er," even if it doesn't make sense. Case in point, things that behave like strings are called stringers. Just get used to it.
Is that the compiler?
No, it's not a compiler thing. It's just you can actually write interface names that don't end in ER, and if you're from a Java background, you're like, what is this "er" thing? It's really driving me a little bit insane. But the idea is it's like these things are supposed to encapsulate behaviors. So, you know, dancers and distancers and gophers. Gophers gof, right? You know, it's trying to get me to think that way, but it falls over. But just like funked, you know? Anyway, how do I get these things together? Like in Java, I want to say something implements an interface. I say, class foo implements bar. But we don't have any classes. And the way that I attached behaviors to types was I implemented a function that had a receiver argument representing the type. So I don't really see a clear way to actually associate an interface with a type. How do I do that? We have to think about it in terms of satisfaction. How is an interface satisfied in Java? Explicitly, right? I attach it with an implement, and then the compiler, by virtue of seeing that implement's keyword, is going to say, okay, I'm going to look up that list of symbols and make sure that you implement all those things. In Go, it's actually satisfied implicitly, meaning that if your type implements all of the methods that are specified by an interface, you are now an implementer or satisfier of that interface. When does that get checked? When you use a thing in the context of an interface. So if I have a function that, in this case, expects a positioner, and I pass it a point, I'm going to take, it's like a point is trying to be a positioner. Let's go look and see if point has all the positioner things. If it does, okay, cool, this code can compile. So it's almost like duck typing. but it's not duck type. So here's a distance function, calculates the distance between two positioners, great. Euclidean distance formula, squares of the distance is fine. Point satisfies distancer and positioner because I implement coordinates and distance to. Obviously it just returns itself for coordinates and then calls that distance between function with itself and the positioner. Cool. Color point can satisfy as well. Color point returns its point. Same thing with distance between. I want to stress that this is about behavior and not taxonomy. Again, you start to think about the hierarchical type system in Java, classes and extensions and implementations. See lots of code over the years where we use interfaces in a very hierarchical way to classify things. Say, okay, it's not just that this thing's a positioner because it behaves like a positioner. It's a positioner because that's a type of thing that I care about, not a set of behaviors that things can do. So that having that implements keyword there, it's kind of like, say class implements Y feels like taxonomy. So would you be comfortable, let's expand the system behind points and say, okay, well now we're tracking animals in a preserve somewhere. Would you like to write the code that says animal implements distancer? That feels strange. And yet, I can make an animal satisfy these things. It doesn't seem too strange for an animal to have a method that tells me its coordinates or its distance to a position on a map. But now, by virtue of implementing those methods, I can actually use this type in any of the contexts that expect those. So I can use points and color points with distances. I can also use animals. I can say, hey, what's the distance between a penguin and a seal? Or what's the distance between a penguin and an arbitrary point on the map? Now maybe this doesn't even seem so special. I don't have a slide for this, but think about it. Readers and writers. Readers and writers are interfaces. A reader can read a slice of bytes. A writer can write a slice of bytes. Anything that satisfies those behaviors can be used in the context of a huge library of functions that know how to work with readers and writers. And as soon as you say that an animal can read a slice of bytes, all of a sudden you have all this extra code that knows how to work with animals. So it's not quite some of the benefits that I like to get out of, say, the closure language, where if I write data and just use the basic data structures, I have hundreds of functions that I can work with, as opposed to in Java, when I create a new type, I have exactly no methods that know how to work on that type, and I have to create them all. It's sort of a happy medium in between those two. It's very easy for me to make my data become available in context of behavior, that behavior was never actually... When they wrote the libraries for readers and writers, they never thought I was going to be using penguins, right? And yet, as long as a penguin can read or write a slice of bytes, all that code's available to me now. So ponder that a little bit, and you start to come up with some interesting applications. You have to go write some of this code. Even if I've listened to several talks talking about how awesome interfaces were, and I'm like, I don't get it. And then I went and wrote a bunch of code. It's like, oh, this is amazing. So hopefully you'll have the same experience. Hopefully it won't take as long for you. Okay, now let's talk about concurrency. First I want to define terms. Concurrency versus parallelism. They're not the same thing. Parallelism, simultaneous execution of work to perform many things at once. You can only do this with as many processors or cores as you have. You only have 4 cores, you can only do 4 things right now, simultaneously. Concurrency, composition of work to manage many things at once. You can do as many of these as you want simultaneously. Think about, you're sitting at your desk, you're writing some code, you hit a block, you go check email, you see an email that reminds you of something, you walk down to the next desk, talk to your colleague about something, then you realize what your problem was, you come back and write some more code. That's concurrency. You are concurrently managing multiple streams of work and switching between them. and coordinating with other streams of work at defined points. Now, if I took myself and cloned me, and I had 5 of me, and one of me was writing code, and one of me was checking email, and one of me was talking to my teammate 2 desks down, then that's parallelism. That's all I'm going to say about it. Rob Pike talked about this for an hour. I encourage you to watch that. That's one of the best talks I've ever seen. Concurrency is not parallelism. So how do we do it in Java? In Java, we do it with threads. Threads are managed by the OS. You create a thread, you pretty much know you're going to get a process. At the OS level, they share address space with other threads in the same parent process. Go uses Go routines. Go routines are managed in user space by the language runtime, and they get multiplexed onto a pool of operating system threads. How do you get these things to work together? Well, believe it or not, it doesn't matter what you're using, what abstraction you're living at concurrency-wise. You dig it far enough down under the covers, you're using shared memory and locking to actually synchronize on things. Lots of cool abstractions built on top of that hide this from us now, but it's still there. You can't get away from it. It's just the way the Java memory model works. In Go, you can share memory, and there's a package called sync that allows you to do this, but there's actually a better way for most complex concurrency-based tasks. And it's expressed through this idea, do not communicate by sharing memory, instead share memory by communicating. So what does that look like? So first of all, Go routines. I have a function f that's going to print itself out basically 3 times. I call it synchronous, fine, we've been doing this all day. I prefix that with a Go keyword, it now runs asynchronously. This statement immediately returns, kicks off a Go routine, goes on about its business. I can also go asynchronous and anonymous, so declare a function and call it immediately in the context of a Go statement. Okay, great, we can spin off code. Now how do we communicate with it? Through channels. So here's another place that we make something. We're going to make a channel that will contain strings, and so I can send string messages on this channel. Inside of this Go routine, I am sending a ping message to the messages channel inside of the main function, which is on the main Go routine. Everything runs on a Go routine. So we have 2 Go routines here. And here I'm receiving a message from the channel. Things to note. When I send to a channel, I block until someone receives from the channel. So I'm running my code, I send. Code, receive. Those things meet, exchange message, and then go on about their business. So this is a synchronization point. It's a very natural, understandable synchronization point. And it's a little bit harder to get this wrong than it is to get synchronized blocks and things of that nature right with Java and threading. You don't have to block. You can actually create channels with a buffer size. So in this case, I'm saying this channel will hold 2 things, which allows me to send twice before I block, allows me to receive twice before I were to block. So now let's bring 2 Go routines together. We have a worker function. I'm passing into that worker function a channel called done that's going to indicate whether I'm done or not with my work. It prints out working, goes to sleep for a second, prints out done, and then notifies the done channel that I'm done by passing in a true. In my main function, I create that done channel, spin off a Go routine with a worker, and then I receive. And so what this is going to do, kick the Go routine off and then block. This code's going to run, that message is going to come through too, this is going to unblock, and the program's going to terminate. So now I've got 1 Go routine, 2 Go routines coming together, finishing some work together, moving on. What if I want multiple things to work together? So in this case, we're going to make 2 channels, C1 and C2. We're going to create 2 Go routines. The first Go routine sleeps for a second and sends a 1 to the first channel. The second one sleeps for 2 seconds, sends a 2 to the second channel. Then we use a statement called select. What select allows me to do is wait on multiple synchronization points, multiple channels. So in this select statement, I'm going to say, okay, I'm going to wait on a receive from C1 and a receive from C2 simultaneously. Whichever one shows up first, I'm going to handle that message and then jump out. And because I have this wrapped in a for, it's going to do this twice, which allows me to receive both the messages eventually. So what's a really common thing to see if you've got sort of a message processor is what you end up with is an infinite loop that has a select that's receiving on multiple channels, and as things come in, it's handling those, looping back through, and eventually you have a condition where if you receive a certain message, it will get you out of that block and allow you to shut a process down. We can also close channels. So job channel for sending work here has a buffer size of 5. Done channel indicate that all work's complete. Here we are receiving jobs. Notice that we have 2 returns. We have J, more. More in the second position is going to indicate whether the channel is open or closed. So I'm saying if there are more jobs, so if the channel is open, receive something from J. If more is closed, I'm going to assume that all the jobs are gone, and I'm going to send true to the done channel, which drops me out of this. And then send all the jobs to the worker, close the channel, block and wait. Whenever that worker's done, I'll receive that message and move on. And last piece of syntax around concurrency, range is overloaded to work with channels as well. So if I range over a channel, then I'm going to receive until there's nothing more to receive, and I either block or when the channel's closed, I'll exit this loop. Why do I like this? Because I like to draw concurrent processes on a whiteboard, and when I draw a concurrent process on the whiteboard and I try to write the matching Java code, it's like I want to shoot myself. When I try to write the matching Go code, it actually almost looks like what I drew. And why is that available to me? Because the syntax is built into the language. It's not a bolt-on library that you're trying to work within semantics that were defined years ago. It's like, okay, let's handle concurrency right now and handle it in the language. This isn't the only language that does this. You see this in Erlang as well. I've started picking up Erlang in the last couple of weeks, which is mind-bendingly fun. But as it turns out, I think Erlang is actually microservices before there were microservices, but that's another conversation for another day.
These channels, do
Yeah.
you have multiple producers, consumers, or do you have to add multiplexers or demultiplexers on them?
You can have multiple senders and receivers, yeah. Most anything that you can imagine wanting to do, you can do. Now, it is still possible to write bad code, but there is a nice tool called the race detector that will allow you to at least analyze your code and find out if you've done obviously silly things that will get you into trouble. Okay, so finish up with tooling. So let's say you actually want to go write some of this code. I'm going to touch on 4 different areas: build tools, dependency management, testing, and editors, just to kind of give you a feel for what's out there. So you want to build some code. Obviously, you need a workspace. Your workspace is also called your Go path. And you're going to have in there a bin directory, which is where all your executables end up. Very common to have go path/bin on your path so you can run stuff that you've created. Package directory, where all your object code ends up. Source directory, where all your source code is. Many different thoughts around structuring the Go path and how it relates to version control. What I tend to do is have multiple GitHub repositories within a single Go path, and that works well for me. Others like to have a single repository for Go path and switch them around. You kind of figure out what works for you. So there's my Go path. I compare the Go tool to Maven, just to bring it back into the Java world. So compile code, Go build, knocks that out. go install will take you all the way to install and create a static binary. Oh, by the way, I forgot to mention, everything's statically compiled and linked, meaning you get one binary. How do you deploy a Go program? You ship one file. It's kind of nice. But there's no dynamic linking, so writing plug-in type architecture is challenging. Running code. Go run. This is like compile it, run it, and throw it away. Go test. Testing is built in the language. This will run your tests. Touch on that in a second. Go get. May even anything. Downloads all your dependencies. Go funct. What does go funct do? It formats your code. How does it format your code? It doesn't know what style of code I want. The Go style was decided. Believe it or not, there are no language syntax style formatting wars in the Go community. It's like the Go team said, here's what we want Go code to look like. We're going to build a tool for it. And everybody just said, okay. I mean, it's the oddest thing ever. Like every other language community I've been in, there's like these flame wars around how you format your code. It's not there. It's like, maybe we should have just all built a tool that automatically did the right thing on day one. Now, I do have to say that it's tabs and not spaces. So if that bothers you, you're going to be just going to be bothered for a long time. You're going to go down this road.
So they are standardized on the screen size now that works for them, 40 or 80 or something.
So basically, yeah. I mean, the cool thing about it though, you go messing around on GitHub looking at Go code, it all looks the same. Like you don't, like I'll move between projects in different languages and you can see the very distinct styles across teams. And you get comfortable reading one style, you go to another style. It's like all Go code looks identical. The Go code in my company, the Go code outside my company. It's like, oh cool, it's just all, it's
yeah, it's just
one
one
less
start
thing.
with all lines with like 4 characters. And then
I can't remember, what is the line length here?
79.
I've never noticed. Granted, I'm always using like this massive HD screen, so. Put it this way, I've never gotten very pissed off about it, so. Dependency management. So I said that there was consequences to go get, and the go get always pulls master, which means that you're always depending upon master. And of course, what you're supposed to do is make sure that master is always stable, and it'll be okay. But everybody doesn't do that. So what's your first option? So kind of the go-to option that this is Rob's is just manually vendor your dependencies. Like pull down the code, check it in the source control, and you know you're locked down. To me, that feels like a step back from what I'm used to. So there are various options that people have sort of invested in. One of them is called GoDep. This is the one I have used the most. Although some of our teams have used this in anger and have found some shortcomings with it. Basically what GoDep is going to do is vendor your dependencies into a folder and keep track of the SHA for each of the head commits for what you pull down. So you pull down your code with GoDep save, you compile your code, it works. You know that those dependencies are not going to change unless you explicitly go in there and decide, I want to go up to the latest version, and then you can relock. And it does this through a metadata file, which says, okay, for this import path, it's this SHA, all the way down. For the small projects that I've worked on, this has worked quite well. But I'd point you to some mailing list discussions around larger projects that have had frustration with this. Okay, testing. Testing's built in. If you really want to think you're taking a step back in time, you look at the testing framework. So any function that takes in a pointer to a testing T is a test. How do you check things with ifs? It's like, okay, if this is not what I expect it to be, then I t.error f, and that's how I make a test fail. And that's basically it. And believe it or not, there are people out there who think that this is all you need. And more power to them. Some of us disagree. Ansi, that I talked about earlier, who's one of the primary guys on Diego, we use a lot of BDD style at Pivotal, and he took it upon himself to write a BDD framework for Go called Ginkgo, and then a matcher library called GoMega. You bootstrap the framework as a test. So I have a test here that takes a testing.t, that registers a fail handler, and then runs the specs. So then I'm able to write code like this. So describe machine with a func, it should work, new a thing, and then say, okay, omega m, this is my assertion, should not be nil. Cool. Oh, by the way, omega is option Z on the Mac. I don't know how to do it anywhere else. But you don't have to use omega. You can use, I can't remember what the actual non-shorthand name is, but this is all over our stuff. You can do context, so I can say, okay, when the machine has been serviced, and then have a before each that says, okay, every time I run through a test in this context, initialize this machine to this state, and then run through the various matchers. So I'm going to say, okay, assuming that it's been serviced, then I should have stuff in inventory. And there's a whole list of matchers out there. A lot of the stuff that you would expect to find in like a Hamcrest type library. Okay, last stop, IDEs and editors. Anybody use Atom? A couple folks. So Atom's the GitHub thing. It's like, let's write an editor in Node.js, see how that works. It's actually kind of cool. A colleague of mine at Pivotal, Joe Fitzgerald, he decided to write a Go plugin for Atom just to see what it was like to write a plugin for Atom. You write everything in CoffeeScript, which is kind of interesting, but this has actually become one of the more prevalent plugins out there. I started using it just to give him feedback, and he did such a good job that this is my go-to editor for Go. Before that, it was Sublime Text. Go Sublime plugin, super popular. Believe it or not, there is a plugin for IntelliJ. And I met the author of this plugin, super sharp guy. And pretty much everything you would expect to be there from a Java perspective is there from a Go perspective, including tight integration with the debugger. So if you like IntelliJ and you want to write Go code with IntelliJ, this is a nice choice. If you're a Vim person, Vim Go, super popular. Is there an Emacs set of I don't know any Emacs Go programmers. So it just doesn't seem to match up very well. If you're not using something that's not Vim, you're using these other deals. So I use Vim a decent amount, so I keep this installed, but I still tend to go to Atom for most things I do. Okay, and that would be that. So any questions? I noticed that I didn't go off any rabbit trails and we actually got done on time and covered all the content, so that was a good thing.